All right, guys, so today we're going to talk about the intermediate value theorem. So we're going to use a very real-world example first to explain this concept to us, and then we're going to take this example that we're using with Uber, and we're going to apply it to a more calculus kind of a function in a minute. So what you can do, actually, is pause the video for a second and see if you can fill out all of page 1 of this worksheet on your own, because it doesn't really have a lot to do with calculus. It's more just reasoning through the situations. So pause the video, read through all of the questions, see if you can come up with some sort of an answer, and then we'll talk about what those mean as we go through. So hopefully you guys went through and read all the questions. So let's talk about these ideas. Hopefully all of you guys know what Uber is, or you've used Uber before. But some things that you have to think about as an Uber driver. So if I was an Uber driver, the first thing I would think about is the number of miles I have to travel, right? That's super important. The number of miles I'm taking somebody. I'd have to think about the cost of gas. Probably the number of passengers, too, that I can fit. Maybe the amount of time, the time it takes. Or even maybe insurance costs. So there's lots of different factors that go into being an Uber driver. And in terms of how much you're earning, how much each ride costs, the time of day that you're traveling, all of that factors into an Uber ride. So let's go through a couple situations. When you pick up your first group of tourists, your trip odometer reads 0 miles. So right now, we're at 0 miles. When we drop them off at the Statue of Liberty 40 minutes later, the odometer reads 17.5 miles. So must there have been a time during the trip when the odometer read exactly 8 miles? Well, I don't know about you, but if you're driving in a car, your odometer is not going to just start at 0 and end at 17.5. It's going to gradually work its way up to 17.5. It's never going to just kind of jump there. So yes, we have to have hit exactly 8 miles, because you can't skip over 8 miles to get to 17.5, right? You can't skip over distance. Right? So in a more calculus function or calculus definition, we would say that distance is continuous. Distance is a continuous function. Okay, so because it's continuous, we know that we have to have hit every single mile and every single quarter mile and every single hundredth of a mile. We have to hit everything between 0 miles and 17.5 miles. Okay, so we can guarantee that. It's guaranteed. Because it's continuous. Okay, now this idea of continuity is going to be very, very important here. Okay, because if we had something where maybe we could jump or break, so sometimes you're going to have functions that aren't continuous, you're not going to be able to guarantee that. But if something is continuous, we can guarantee it. So let's look at a different example. At 3 p.m., you're hired by a group of art teachers to take them from Long Island to the Museum of Modern Art, I think that is, right? Which is 50 miles apart. Okay, so we're going from 0 miles to 50 miles. And it's over the course of an hour. So also in terms of time, right? Time is going to be continuous either. We can't just jump over time or transport in time. There's no time travel right now, or we can just jump over different parts of time and forget about it. Okay, so our first question is it possible that at some point during that trip we were 53 miles away? Okay, so we're going 0 miles to 50 miles. Is it possible that maybe at some point I was 53 miles away? Well, let's say from point A to point B, if this is 50 miles, let's say I kind of maybe went this way and came around, right? So that could totally be 53 miles for the path that we took, right? Maybe up at this point right here, this distance actually was 53 miles. Okay, so if I were to have maybe taken a little bit of a roundabout way, or maybe I made a stop along the way, the GPS took us on a detour, whatever it was, if we didn't take a direct route, it is possible for us to be 53 miles away. Is it possible for us to be 100 miles away? Well, yeah, but that's a little silly. As long as we're going some sort of a roundabout way or going away from that point and then coming back, it is possible. So yes, maybe we made a stop. A detour, or took the long route. Okay, now it's not guaranteed, but it is possible. Okay, not guaranteed, but possible. Okay. So now the second part. Must there have been a time when I was 53 miles away from the Museum of Modern Art? Must there have been a time? Well, we just talked about that. I can't guarantee it, but there could have been a time. So no, it's not definitely guaranteed, right? We could have just gone straight there. Okay, so the idea of the fact that it's possible, but it's not guaranteed. Okay, and here we're thinking about the interval from 0 to 50. Okay, so on that interval from 0 to 50, it is continuous, but I cannot prove that I went 53 miles, even though I could have. Okay, so we're talking about here the actual proving of it. Okay. All right, number 4, during your 8-hour shift, you made 12 Uber trips. Your first trip had 2 passengers and your last trip had 4 passengers. Should we assume that one of your trips had 3 passengers? Well, number of passengers, I would say, is not a continuous function, right? Number of passengers is not continuous. No matter what, it's not continuous. So therefore, we cannot conclude that. Okay, could it have happened? Yeah, it totally could have happened, but we cannot prove it because passengers is not continuous. Okay, so what is this going to kind of mean in terms of calculus? Well, there's a couple of things. This is where what comes into play, what we call the intermediate value theorem. Okay, the intermediate value theorem is used to say that if we have a continuous function, we can prove that those y values are going to exist in between it. It doesn't necessarily mean that those are the only y values, because we could go outside of that range, like we did with the 53 miles, but it's used to say that everything in between those y values in a continuous function will be reached. Okay, so the IVT is used to prove that a certain y value will exist. Okay. So there's a condition that has to apply here, though, and you guys decided that. The condition is that the function has to be continuous. So if a function f of x is continuous, and it's got to be on the interval AB. Okay, so it might not be continuous the entire time, but it's continuous for the part of the function that we're looking at. Then, and this is our calculus definition here, then f of x must hit every single value between f of a and f of b. Must attain, or we can say hit, every y value between f of a and f of b. Okay, so whenever you're doing a question that involves the IVT, you have to make sure that you always tell me what function you're talking about. Remember, we can never say the function. We have to specify which one. And you have to tell me that it's continuous on this interval. Okay, those are kind of the three conditions that have to play out. Okay, so couple things you want to do. Every time you are talking about the IVT, the first thing you want to do is verify the condition. Verify the condition. The second thing you want to do is you want to find f of a and f of b. Okay, and then you want to make your conclusion. And that conclusion, you're going to want to make sure you write a sentence. Okay, and I'm going to give you kind of a little filler for your sentence every time you do it, just like we kind of did with continuity. Okay, so we're going to start out by saying, since the function, whatever your function is continuous on whatever our interval is, right? And f of a equals this, and f of b equals this, the IVT guarantees that, and then you're going to finish your sentence. Okay? So that's kind of the way that you're going to write these sentences every single time. Okay? So let's talk about this now. Let's dive in. So sketch a graph that does not satisfy the IVT. So we know, we talked about, it has to be continuous, right? So on A, from all the way from A to B, my function has to be continuous. So let's draw one that maybe has a little jump or a gap, right? Actually, I'm going to go like this. Because you'll see right here, these y values in between here are never going to be hit. Okay, so our function was not continuous, so we couldn't guarantee that every single y value was touched between f of a and f of b. Okay, and f of a is over here, and f of b is down here. So we cannot conclude these ones were hit and these ones were hit, but the ones in between were not. Now let's sketch one that does satisfy it. So from A to B, our function has to be continuous. Okay, so because it's continuous, I know that every single y value in here is touched as part of my graph. Okay, so let's apply it. The function h of x is continuous on the interval -3 to 7, and h of 3 is 10, and h of 7 is -2. So let's kind of sketch this graph here. H of -3, oops. H of -3 is 10, so let's just put a point up there. That's -3, 10. And then h of 7 is -2. Let's put that down here. 7 is -2. Okay. Is there a guarantee that some value of a in the domain such that h of a equals 1? Well, right here is 10. Right here is -2, right? So if my function is continuous, right, I want to know, is there a place where the y value is 1? Y value is 1, yeah, right here. Now, I don't know exactly where that is, what x value it's at, but I know that somewhere in this graph, because it's continuous, I'm going to hit the y value of 1, okay? So let's practice writing our sentence. Since h of x is continuous on the interval, we're using -3 to 7 here, okay, and h of -3 is 10, and h of 7 is 2, the IVT, and you can write IVT on the calculus test, they know that. The IVT guarantees there is a value A in the domain such that f of A equals 1, since, okay, we can show that f of A is in between -2 is less than or equal to 1, which is less than or equal to 10. Okay, so that's how we know. And that's how your sentence is going to kind of be put together every single time you're doing these. All right, let's do one more example again, and then we'll be done. Use the IVT to prove that there's one solution to this function. So one solution, okay, is kind of like showing that there's like a root here between x equals 1 and x equals 2. Okay. So let's find f of 1 first. F of 1, I'm going to do 1 to the third plus 1 minus 5. Okay, that's going to give me 1 plus 1 is 2, 2 minus 5 is -3. So f of 1 is -3. Now let's find f of 2. 2 to the third plus 2 minus 5 is going to give me 8 plus 2 is 10. 10 minus 5 is going to be 5. Okay, so f of 1 was -3 and f of 2 is 5. Now the question is this a continuous function? Well, we know that quadratics are continuous functions, right? We know that that's because we know what it looks like. Or sorry, not a quadratic, this is a cubic function. We know that a cubic function is going to be continuous. So using our idea of functions, we already know that step. Now I know that f of 1 is -3 and f of 2 is 5. I want to know, is there going to be a place where f of A equals 0, right? So the answer here is going to be yes, because 0 is going to fall in between -3 and 5. Okay, since it's continuous, we have to hit every y value in between that. So let's sketch out a little picture before we write our sentence. So if I have 1, -3, right? And then I have 2 and 5. If I'm going from point A to point B, I'm going to have to cross over my x-axis somewhere, which means that my y value would be 0 there because it's continuous. Okay? So let's write our sentence. So since x to the third plus x minus 5 is continuous on the interval 1 to 2, and f of 1 is -3 and f of 2 is 5, the IVT guarantees there must be a value A such that f of A equals 0, since 0 is between -3 and 5. Okay? So your sentence is going to look almost identical every single time that you do it. Does it have to be word for word the exact way that I write it? No, but there's some key things you have to have in here. You have to have that it's continuous, you have to have the interval, and you got to tell me what my two endpoints are. Okay? This statement is also pretty important too, because it's showing me that you're recognizing that that value is in between both of your endpoints for your intermediate value theorem. Okay, so that's your little intro to the intermediate value theorem, and we will practice some more on that in class.